Welcome to the panel session on whether or not we need a Jupiter to form an Earth. My name is Rob French. I'm a researcher at the SETI Institute, and I'll be your moderator this morning. To my right, we have Rosalie Lopez. She's a senior research scientist at NASA's Jet Propulsion Laboratory, an expert on volcanoes on Earth and planets, and has worked on both the Galileo and the Cassini missions. To her right, we have Kevin Grazier, who I'm sure you've heard speak many times this weekend about his interactions with the media and his work on Battlestar Galactica and other TV shows. But he also has been for 15 years an investigation scientist on the Cassini-Huygens mission to Saturn and Titan, and has performed research on long-term computer simulations of solar system and its evolution. To his right, we have Martin Still. Martin is the director of the Kepler Guest Observer's Office and has interests in planetary accretion, compact binary stars, black hole physics, gamma ray bursts, and exoplanet detection. And we're going to have Rosalie go ahead and open up our panel session this morning.
Okay, well, good morning. This is not exactly my topic, but what I'm going to try to do is set the stage so that my fellow panelists can talk a little bit more about it, because it's more their area of expertise. But I'd also like us to expand on the topic a little, and particularly looking at the questions of other solar systems, and do we need a solar system like ours in order to have an Earth as we know it? So the idea behind this team, the first idea is Jupiter our friend or our foe? So did Jupiter help create the Earth or make the Earth what it is now? Or did it actually had a bad effect on our evolution? And these are very interesting questions, and it's all to do with the formation of the solar system and how Jupiter can have an effect on how many impacts the Earth has. Now, as a planetary geologist, I do study impact craters. And we find many impact craters on many bodies in the solar system. And is a question we are always asking is, what's the population of impactors? Now, on Earth, we don't see many impact craters these days because the Earth has a lot of erosion, has plate tectonics, a lot of processes that actually have erased the craters from this period of heavy bombardment that happened billions of years ago. But the question here, the first question is, what was the influence of Jupiter? And back in the mid-90s, a planetary dynamicist called George Wetherill came up with a model. He did computer simulations and came up with a model that Jupiter actually helped clear out a zone of potential impactors that could impact the inner solar system. And so that got sort of popularized and entrenched in planetary science as the idea that Jupiter acted as a shield and so protected the Earth from many impacts, and therefore maybe life could have evolved on the Earth because we didn't have as many impacts as we would otherwise have had. But this idea has been challenged, and in fact, around 10 years later, we have better computer models, better computing facilities, and other people came along and said, well, no, this is not quite right. And in fact, Jupiter may actually have caused more impacts to happen on the Earth than if we didn't have Jupiter. And Kevin can talk more about this, but the part of the question here is that it's not just one population of impactors. We have comets from the Oort cloud being some of these impactors on Earth. And in fact, Wetherill's idea may be right for those objects. But then we also have asteroids from the asteroid belts, and we have short period comets whose origin is just beyond the orbit of Jupiter, between Jupiter and Neptune. So we have several different populations of impactors, and we have these competing models actually saying, well, maybe Jupiter protects us or doesn't protect us or makes the situation worse. So where do we go from here? And this also opens up a more philosophical question that science only evolves because someone comes up with an idea and then somebody else comes up with better data, better ideas, better models that actually say, no, this wasn't quite right. And often there is some truth in the first idea, but that has to be adjusted so that it becomes a better idea. So with that, I'm going to turn it over to Kevin.
Thank you. Rosalie just said something that I would say, she said it correctly, that most people say incorrectly. And she made the point that in 1994, George Weatherall wrote a paper that said Jupiter clears out a reservoir of comets, and that's absolutely true. In fact, that was my PhD dissertation, was we put 100,000 particles between Jupiter and Saturn, watched them evolve, and said, does anything last? Now, the purpose of that was to see, could there be other asteroid belts? Because back when I did this work, the observation tools that we had weren't as sophisticated as what we have now. And remember, things in the outer solar system, though they may be largely icy, are dark. Comet Halley showed us that something can be mostly ice and still be almost jet black. So was the question, could there be asteroid belts out there that we just can't see? And the answer was no. Anything put between Jupiter and Saturn, the region is so dynamically unstable, they get kicked out on very short time scales. We're talking 10,000, order of 10,000 to 100,000 years, they're gone. And in the solar system, that's a blip of an eye. But that's not how Weatherall's initial paper has been handed down. What came of his paper, and there's probably this stemmed from a mistranslation and done for the book Rare Earth, the book that claims that Earth we're unique, or close to it. What they said is that this got handed down is Jupiter acts as a shield from comets from deep space. The notion that we need comets, that we need some protector to shield us from comets coming from distant space. Now, that leads to two thoughts why that is just a myth, and I'm comfortable and that I not a crackpot in saying it's a myth simply because it's so heinously wrong that it's never what George Weatherall said. So I'm not slamming George Weatherall's work in saying that. I'm slamming the translation, and I'm slamming things that get taught dogmatically without question where they came from. If you look at there are two populations of comets primarily. We have what are called short period comets and long period comets. Long period comets, if you look at the inclination distribution of comets, it's basically, it's completely random. It's a cloud. There is a reason it's called the Oort cloud. That implies a shape. So the inclination distribution of comets coming from the distant parts of the solar system are all over the map, and Jupiter doesn't even come close to many of these objects. It can't shield what it doesn't come near. The second population are the short period comets, and those generally are more Kuiper belt-like, and they're more in the plane of the solar system. And for those, if you take Jupiter's sphere of influence, the region around it where you are gravitationally dominated by Jupiter as opposed to dominated by the sun, and project that onto its entire orbit, it's puny. Jupiter is not a shield. That said, and Rosalie also mentioned, is Jupiter a protector or a foe or a danger? And the fact is that when you in fact take these particles and you place them between the outer planet gaps, what you find is that they generally do get kicked out, which George Weatherall found. He found most actually, in the presence of a full-size planet, get entirely ejected from the solar system. And that's the same thing that we find with a much, much more accurate model. But that said, what gets ignored is that many of these actually get kicked through the inner solar system first. Now, astrobiologists say that we need volatiles, and the primary volatiles we talk about are water, carbon dioxide, ammonia, and methane, from the outer solar system to be kicked into the inner solar system to create the necessary building blocks for life. So what happens is that although Jupiter tends to kick out these particles and out of the solar system completely, many of them pass to the inner solar system first. So Jupiter is less a shield and more of a sniper. And in fact, in the situations when you have objects coming from the deep solar system and they interact with Jupiter, half the time Jupiter boots them out, half the time it brings them into tighter orbits, which are actually more likely to impact Earth, giving them a second chance. So what we're finding out with more accurate models is that this Jupiter as a shield notion is really just, it's a mistranslation of an initial result that got taught dogmatically for years. And I'm done proudly.
Okay, I just want to point out that at 11:45 the football starts. So I'm going to get a bit glassy-eyed, and it's not because I'm not listening, but I will be looking at my smartphone every now and again. And at the end, if you want to have questions and conversations, I will be running David Beckham-like in that direction towards the sports bar, and you will find me there.
What do you mean about football? The NFL doesn't start till for months. I don't understand what you mean. You mean this thing you call soccer?
The thing you kick with your foot. That one.
Yeah, well,
Anyway,
Field goal.
put on my local sports
I
team.
believe I believe the reason I've been invited on this panel is because I work primarily on the Kepler project. And as you know, as you've already heard, there's enormous synergy between the goals of the Kepler mission and the goals of the SETI mission. The Kepler goal, to sum it up in one sentence or two sentences, is to measure the frequency of Earth-sized planets around other stars, particularly those planets which exist within the habitable zones of those stars, that region where the temperatures are just right for flowing water to occur upon rocky surfaces, just like we have here on Earth. The purpose of the SETI mission, and I'm paraphrasing because I had to look this up on the website last night, is to understand the origin, the nature, and the, I've forgotten the word. Distribution. Thank you. Of life in the universe. And so, of course, there's a huge overlap there in interest. SETI is very interested in taking the Kepler sample of planets and understanding the possibilities of life upon those planets. And so this question about whether Jupiter is actually required for life on Earth or acts as a shield for preventing bombardment upon the Earth's surface, or even induces more bombardment, is an extremely interesting one, both for the Kepler project and the SETI scientists. I absolutely don't know what the answer is. I'm interested to sit here and listen to the arguments. What we're interested more is measuring the distribution of these planets in a statistical sense, and this whole question about whether small planets close into the stars, close or within these habitable zones, are accompanied by large giant planets like Jupiter further out, is one that we can at least approach answering. How common is that situation? Now, the reason we can't necessarily answer that positively is because Jupiter's orbit is many years. Earth's orbit, of course, is 1 year. Jupiter takes many years to orbit the sun. So Kepler detects planets by the transit method. Is this working? Yeah, okay. Okay. So if a planet like the Earth orbits its star in a year, we can only observe one transit once per year. Then we have to wait another year, and then we'll see another transit-like event, and then we can go, oh, that may be an orbital period. We need to see it again, a third time, to actually confirm that that period, that event is coherent and it's happening at the same time for that particular object. Otherwise, it just could be random noise, something statistical in the data, or some other astrophysical event fooling us. So we have to see a transit at least 3 times to believe it, or start believing it. So for an Earth-sized object in an Earth-sized orbit, we have to wait 3 years. So Kepler's only been in space and operating now for 3 years. We are just now getting sensitive to those kinds of objects. But now think about a Jupiter. That orbits once every 8 years. 12. Sorry, 12 years. Excuse me.
No problem.
So we have to wait 36 years in order to verify that that is a bona fide planet around another star. But Kepler, unfortunately, has a finite lifetime. It only is going to operate somewhere between 10 to 12 years because there are consumables on board. There's fuel. So once that fuel runs out, we can no longer operate. Kepler will just start spinning. We won't be able to point it anymore, and that'll be the end of that. So unfortunately, Kepler is probably not going to answer this question very well in a statistical sense for thousands of planetary systems. It's going to understand the inner dynamics of these systems and the inner populations of these systems incredibly well, but it's going to do not such a good job on the planets further out. It's going to provide something. It's going to provide speculative results. You're going to see things which transit once, and scientists are going to go, well, maybe, and they're just going to use that information as priors and as starting points and try and make something out of that. We also have a second method for detecting outer planets, which is by timing those transits that we detect. The gravitational influence of other planets within the stellar system further out actually change subtly the times at which the transits of the inner planets occur. So we can also see the effects of large, massive planets further out in these systems without actually seeing them themselves, just because of the gravitational effect they have on the inner planets. But again, we're only going to have 10 years worth of data and not 36 years worth of data. So it's going to be incredibly speculative. So the message here really is that Kepler is not the answer to this particular problem. Whatever comes after Kepler, whatever work is done post-Kepler, whatever the legacy of Kepler is, whether it's other missions, other observations from Earth or space, other ground-based computational calculations, that is the legacy of Kepler in this particular problem. Okay, that's enough from me.
That's good.
Hello. If I can break in for a second, I didn't introduce David at the beginning, so I'll introduce him now. David Sommers is a senior research scientist at the SETI Institute, and he investigates a wide range of chemical reactions that are either needed for life to begin, that may affect whether life can exist, or that might be used by scientists to recognize life elsewhere. David?
And I take this from an astrobiology perspective. That's what I am. I'm not really up on the dynamics of planetary formation, so I'm sure if I get something wrong, I can count on my colleagues left to shout derisively at me. So, and in fact, they did a good job of covering the issue of getting smacked, as we like to call it technically. And to the degree that you're blowing away the atmosphere or boiling the oceans or melting the crust, for life, that's generally considered bad. That's generally considered bad. However, and Dr. Grazer touched on, there are actually some good things potentially available, and that actually has to do with water. Everywhere we look on Earth, we find water. The strategy to search for life is follow the water. Water is an essential habitat for life, essential requirement for life. And when your solar system's early on, what happens is, of course,
Can you hear in the back? Are the speakers on? Can we get somebody to
Can
go
people
find the audio guy, because he
all right, I'm
escaped?
going to speak louder. Does that help? Okay. So you're in vacuum. Sun heats up stuff in the inner solar system. The volatiles, i.e. water, get lost. And they tend to go out to the outer solar system past what they call the snow line. That's where you get a lot of ice. But all this is past what they call habitable zone, where you want to be for a Earth-like planet to have liquid water on the surface. So somehow you need to get all that water back in at some point. Now, there's a controversy about when that occurs, and I won't burden you with that. But one way in which it can occur is comets come in from the outer solar system. Well, one way this happens is that little gravitational tugs, I guess little's relative, change the orbits of these comets and bring them in, and then that was touched upon. And that is actually one of the two main theories about how water came in. So the question is, and this probably applies more to whether you have Jupiter-like planets anywhere, because I think it doesn't really matter so much whether if Jupiter was further out, it would still scatter comets in. So we just mean, do you need gas giants in general? And it certainly would make a difference. I don't think we know enough to say good or bad. Also, you need some of the waters made early on before you form planets and bigger bodies. But even that, you need some mixing of the dust that's occurring in the accretion. And I can't help but, like I say, I'm not an expert, I can't help believe that Jovian's accreting would help mix the solar nebula and bring water-bearing dust closer in to be accreted to the Earth, or perhaps, small planetesimals. Generally, I think it's safe to say that, so the gas giants can work to bring water in, and water is important. Now, one problem with the Lonely Planets book was what it did is it looked at the one case where we know life is, looked at all the properties of that one case, and assumed they're all important. And to some degree, that's one problem we come into worrying about whether we need a Jupiter for Earths. And by Earths, I mean habitable planets, much like we have, is where there's a real tendency to, since it's occurring in the one case we know, we think it must be important. I don't think we really know whether you need a Jupiter, you need a Jupiter where it is, or whether you need Jovians as a whole. But again, you can make some cases that it'll certainly make a difference. And in fact, you can also, I will point out, potentially go too far the other way. Some of the Kepler data, and by the way, Kepler's game changer for all this, has been saying that some of the bigger terrestrial planets, 2 to 3 Earth masses, something, look like they have a lot of water. And I mean, this is a lot of water, as in Earth has almost nothing water. We're talking planets that are tens of percents water. That means you've got a surface environment, not only that doesn't have any land anywhere, we're not even talking islands, just open ocean as far as wherever you would go. But the bottom of your ocean, muds where things might occur, are like hundreds or even maybe 1,000 kilometers down, which means there's really no access to solid phases in a way that you have on Earth. Is that good or bad? No one knows. We really weren't even aware that these planets were likely until Kepler, again, big game changer. So unfortunately, I'm sending out a lot of maybes and we really don't knows. But on the other hand, it's what it is. And I guess it just shows what we need to know more than we do. So,
Can I add something? Is that we?
You're not going to shout derisively at me?
No.
Oh, okay.
Well, you ran to me of a good point. Is that, remember, Earth is believed to have been the benefactor of one very monumental impact. And in the early days, Earth had an atmosphere that's probably more like Venus than it is right now, and we believe Earth was struck by an object between 1 and 3 times the size of the planet Mars, and that impact literally blew off our first atmosphere, and then the remaining or subsequent outgassing and impacts, a veneer of material from comets gave us a secondary atmosphere that was then modified by early life. What I think we kind of tend to forget sometimes is that Venus has an atmosphere that's mostly carbon dioxide. Mars has an atmosphere that's mostly carbon dioxide. At the molecular level, carbon dioxide is a much more massive molecule than the other kind of volatiles that tend to form, that are delivered by comets that form our atmospheres. And I think what we're going to find, and if you want to say this is a prediction, fine. I think we're going to find that extrasolar Venuses are a lot more common than extrasolar Earths.
Hello. If I could ask our first question here. Staying within our own solar system, if we didn't have a Jupiter that formed as part of our solar system formation, how do we think Earth would be different? Do we think it would have been in a situation where life could have evolved? would we have, I mean, ignoring the one big impact, which may have been there with or without a Jupiter, right? But in terms of Jupiter sniping Earth versus protecting Earth, the other gravitational effects that Jupiter has had on the solar system, you know, could we be here today if we didn't have a Jupiter?
I'll address that. Well, I mean, the two things I know, one is the bombardment. And in fact, I'll actually maintain that while getting, like I say, getting your oceans boiled off is considered bad, it really isn't. I mean, the bottom line is life formed on Earth because conditions were amenable to life forming on Earth. And if we had come in even 3 billion years ago and been hit by sterilizing, they call it sterilized impact, and people argue about how big a thing needs to be to definitely sterilize a planet, hit by a sterilized planet, the geology resets and life probably reforms. Life forms so quickly in the Earth that it doesn't appear to be all that difficult once conditions are right. So I mean, maybe we might be a little further, might not be quite so far down the road. You know, we might still all be dinosaurs or something like that. But I don't think it would be that big a deal. The water, however, could be a big deal. It's not clear if, for instance, a world that has only one small sea and deserts everywhere can form life. It's not clear that a world that's covered with oceans can form life. And while I don't know enough about predict which way it would go with different configurations of large planets, I do think it would make a difference and it would be important. So I kind of think they would be important, and to be exactly where we are probably requires something sort of like what we have now. But again, it's not clear, you know, the one case, it's not clear we need to be exactly where we are now. So,
if you perform simulations of the solar system and you put a bunch of hypothetical particles between Jupiter and Saturn, Uranus, Neptune, and you remove Jupiter, so you just have Saturn as the innermost Jovian planet, what you find is, what you kind of might expect to find, is that you end up with an asteroid belt that would interior to Saturn, that due to a effect called resonant effects is truncated about where Jupiter is, because Jupiter and Saturn are very nearly in what we call resonance. But you end up with an asteroid belt and a few gaps in an asteroid belt because of the effects of Saturn. But you end up with all that material that's mostly water laden remaining in the outer solar system instead of getting kicked out or passing to the inner solar system first. So something we're still looking at is, instead of Jupiter being a protector, might it actually have been responsible for delivering all the volatiles that we need? So Jupiter, in exact opposite to the current belief that Jupiter is a shield, it could be the requirement that the building blocks for life and for water were delivered here by the interactions, and that if you remove Jupiter, what you get is the outer planets still would have delivered material, but a lot less of it. So you still could have had the conditions for life, but certainly they were probably enhanced by the presence of a Jupiter.
So one other question, and then we'll open it up for questions to the floor. I'm sure that when you mention dinosaurs, there are people in the audience who are wondering about the dinosaur killing impact. And can I just ask the panel whether or not Jupiter had any influence on that asteroid that killed the dinosaurs?
That's something I'm looking at right now, because what you find is that these outer planets clear out their zones. And this is actually, now I'm talking about a paper that the Jupiter as a sniper, not a shield. That's actually, I need to get that out. I'm probably this week or next week I'll get that out the door. I've been sitting on that for such a long time. It's pathetic. But I got another one subsequent to that that's in the dynamics of the outer solar system that looks at that very thing, and it turns out that Jupiter probably didn't have a handle on that, not much anyway, not directly, because what happens is if you simulate the outer solar system and you look at the reservoirs between the outer planets, what you find is that these zones are cleared out by the dynamical influence of the Jovians so fast that they're very short time scales compared to the age of Earth, and certainly very short time scales compared to the formation of the solar system and 65 million years ago when the KT impact occurred. So we have to look for another source region. Where did this object come from, or where did the other objects that have led to major extinction events come from? And based on my work, I have a notion that it might have been what's called the Kuiper scatter disk. but I'm not willing to go into too much more detail because, like I said, that's something I still have to write up.
And I would like to make a comment. And while we have no doubt that the Chicxulub impact did occur, of course, there are people who still argue whether that actually was what killed the dinosaurs or not, or if it was something else. So it's by no means a certainty. There were huge volcanic eruptions around that time, the Deccan traps in India, and there are scientists who argue that that actually was the key factor. And others who argue that dinosaurs were on the way out anyway, and why would the impact or the volcanic eruption or whatever have killed the dinosaurs and not some other species. So there is uncertainty in that as well.
One more thing I want to add about that is when I teach my planetary science class, it's basically a freshman level class, one thing I point out is that you'll hear planetary scientists claim again and again that we study other planets to learn more about Earth. Now, is that really true, or is that what we tell Congress when we want more money? Well, what I point out is you go to use Mercury, you look at the planet Mercury, and you can link that to the death of the dinosaurs, to what Rosalie just said. So if you look at the Chloris Basin, it's a huge impact on Mercury. But if you look at the opposing side, it's all jumbled up because of what's something called geometric focusing. The seismic energy, the seismic waves that propagated out from that impact were refocused into the antipode, the part exactly opposite of Mercury. Now, if you look at the impact that killed the KT event that occurred that certainly I think had a hand in killing the dinosaurs. That was, now, when you look at where that occurred, we're pretty sure the smoking gun is revealed by an impact site in the Yucatan Peninsula called Chicxulub. Now, taking plate tectonics into effect, you look at the Deccan traps, which are in India, and you reverse India, the subcontinent, and go where it was 65 million years ago, and it turns out to be antipodal. It's exactly opposite of where the KT impact was, and it could turn out that similarly to Mercury with the Chloris Basin, that an impact occurred on one side, geometric focusing actually helped to generate, for lack of a better word, the basalt, or it changed the level of a transition that created more magma, and that became the Deccan trap. So one could have led to the other, meaning there's two things that just made Earth a really crappy place to be for a while.
Have we told our audience what the Deccan traps are?
No, we didn't. Go ahead.
Well, they're basically a big lava, a huge eruption of lava that occurred about the same time in a different part of the planet. And as we know, volcanoes can put dust in the air, change the climate dramatically, and that is argued to be what killed, by some, to be what killed the dinosaurs.
I think calling the Deccan traps a big lava flow is sort of like calling the Pacific Ocean a big lake.
Yeah, right.
Fair enough, true. It's huge.
All right, let's go ahead and open it up to questions from the audience. We have a roving microphone. Go ahead and raise your hands, and we will get the microphone delivered to you. We'll start with the guy here in the front with the orange jacket. That's you. But no, there's a microphone coming.
David just kind of briefly touched on it, but I wondered if anybody had anything more to say about just during the accretion period, what an effect of a Jovian planet like Jupiter forming would have on maybe other rocky planets forming, if any at all.
Called you out by name.
Oh, you did? Oh, sorry. Well,
Anybody can answer the question.
okay, I'll say something and they can shout derisively at me. They haven't had a chance to. I mean, I think well, first of all, I will annoy them by pointing out that the biggest lesson from the Kepler view is that you can take all these planetary formation theories that all these people work so hard to generate, get a nice big shredder, and run them into it. So we don't. What Kepler's telling us is we actually don't know near as much about this as we thought we did. We do, I think it's still clear that if you have a Jovian planet, you can't have a planet form just inside of it. Okay, even that's not true.
No, I agree with you. I'm agreeing with you.
Okay,
No, you can't.
that's why you're not shutting dry.
That's why I'm not shutting derisively at you.
So, I mean, yes, it does put out a space where you can't form planets. So if you're Jovian near the habitable zone, where you want to be, actually, you can still have habitable worlds, but they're going to have to be moons, because you're not going to have a planet by itself forming if there's a Jovian 2 near the habitable zone. Other than that, I don't think you can say a lot based on what we know now.
I think it's actually called properly called the Gavin Effect. You've heard of that? The Yavin 4 in Star Wars, there was a habitable moon. And I think people call that the notion of a Jupiter, a Jovian planet in the habitable zone with a habitable moon. I think that's actually called the Yavin Effect.
That's cool. I didn't know that.
So even that, I think, is possibly old news. I think there was a press release out last week at the Anchorage astronomy meeting. I forget numbers now.
Informal thing. The best way is, you fool, that's wrong. I mean,
Well, you're larger than I am. No, the microphone's not working. It's seriously not working.
Then use somebody else's.
All right.
I don't think his is working.
No, I don't think so. So I'll just speak
In
louder.
touch with your inner thespian. From the diaphragm.
Wow. So I forget what the numbers are now, where the numbers are getting silly. I think it's Kepler 36, so the 36th star that we have confirmed planets around. Not planet candidates, but confirmed planets. And so that new system, there are 2 confirmed planets around that star. They're both orbiting within a Mercury orbit, but one is a gas giant and the other is a rocky planet, or close to a rocky planet. And at their closest approach, they are barely 1 million kilometers apart.
so you're busily working to stamp out the last remnants of the old planetary formation theory as much as you can.
I just wanted to point that out, because this whole idea of a giant planet or a small planet not being formed close to a giant planet, at least in this particular example, appears not to be correct.
Okay, well, slight defense to the planetary formation theories, which I've been mocking. It's also possible this thing could have migrated in, which means there's actually the new planetary formation theories say these big planets, and I guess even potentially the small planets, can move around. They can move in. I don't think they can move out.
Yeah, they can.
Okay, they can move in and out. And so this one may have prevented planets from forming near it and then moved into one that had formed earlier away from it. But it's also worth pointing out, no one knows, the assumption is that if you move a Jovian planet into the habitable zone, it destroys all planets in that area. And in fact, before Kepler came along, there was a theory saying that Earths were going to be really rare because we were seeing before that we were seeing a lot of close-in Jovians. And some people are coming to the view that Jovian planets come in as a rule, destroy all the planets on their path in, and just devastate solar system after solar system after solar system. Well, clearly that's not true, but it still does mean that these Jovians move around could have consequences. I heard someone say there's a theory of how terrestrial planets could survive this, but I don't know what it is or understand it. But
There was a recent paper that said that our Jupiter came in as close as 1.5 AU, which I don't buy for a second, but there was a paper that said that. But in a simulation, a paper that I just got the referee comments back for is we made the claim in that paper that we ignored migration in our paper simply because there's no consensus. People, you can say just as many papers that say they moved in or moved out or moved in and out, and how far is completely. So we just said, hey, we know they're here, so we're going to do the simulation to say, and we're going to base our results on what we know. Okay. That said, because of the simulations that I do, and I'm still backlog on getting some of this out the door. What I find is that I don't necessarily think that our theory of planet formations theories need to be modified or changed so much as modified, because what I'm finding in some of my simulations is that some of the delineations we made of objects, we say these are Centaur asteroids or these are this, some of these delineations just don't really occur because there's a lot of mixing done by these Jovian planets and things get kicked out, things get kicked in, and sometimes these processes are still ongoing. So I think that there's just with the Jovians, there's a lot of mixing of material, and I think that we put some things into sort of artificial categories that I think we're going to have to recategorize. But as far as the complete change of our theories, no, probably a modification is probably more in order. Does that make sense? Does that make sense?
Hi, another Oh, another question about
mic works.
this
Ours
one's
don't.
this is great. Another question about planet formation models and sort of going back to before they had to be put in the shredder and just the basic idea of the models. From what I understand, it seems to make a lot of sense that Jupiter would form as big as it is where it is. And so I'm wondering, with all this talk about, is there, could we have an Earth without a Jupiter? Are there models that make us think that it's relatively common to have solar systems with rocky planets without a large gas giant about 5 AU out?
Anybody else want? I'm talking too much.
Well, I think I'll say something, and then he can correct me. I had heard, and this may be old, that MClass stars, which are very interesting because we don't know how habitable, we don't understand habitability around MClass stars as well, because a planet that's close enough to be warm enough to have life is also tidally locked. And so there's a lot of things to be looked into that. The reason everyone's busy looking at them is there's like a whole bejeevers of them. I think it's or 2 bejeevers maybe. There are a lot of them. There are a lot of those guys. And I think MClass stars are going to not have fewer Jovians, right?
True, yes.
And the Kepler, I think, is finding some systems with rocky planets without Jovians, but they just haven't found them yet, right?
That's true.
So I think it's possible.
You also have the M-class planets also, sorry, the M-class stars. M-class planets, that's Star Trek. the M-class stars, in addition to being so close, were a planet to be habitable around M-class stars, in addition to being so close, these smaller stars are more prone to flares. And so you're bringing something in close, and then you're just nuking the crap out of it. So they tend to be sterilized for another reason as well, at least on the sunward side. But back to your question, as far as the Jovian planets, there, our Jupiter is where it is, we believe, because, like you said, that's the most likely place for it to be. It's just outside the frost line, so you're benefiting from more access to solid material, plus more access to the differential velocity needed for impacts. And we believe Jupiter formed first because of a term that one of my members of my committee called capitalistic growth. The rich get richer. You get a little bit of mass, you therefore get a non-trivial amount of gravity, you draw more material, you get more gravity, you draw more material, you get, and it runs away. So, but the real question is, what is so that might be just outside the frost line, might be a preferential place to form a Jovian. I would completely buy that preferentially. Again, there's perturbations. That said, we're still not entirely sure what role migration plays. I mentioned earlier something called resonant effects, and these resonant effects are what create the gaps in the asteroid belt called the Kirkwood gaps, or the gaps. In Saturn's rings called the Cassini division. A moon Mimas that's well outside of the rings creates this gap in the ring through resonant effects. So these resonant effects with these Jovian planets in concert with the material that's already in the disk will throw things out and pull these things in. So we know migration is possible. What role that plays in bringing these in or having them migrate out is still TBD. Am I answering your question? Sort of. In a roundabout way, at all?
Yes.
The answer is maybe.
Sounds like it.
All right, we have the guy in the back with the white jacket.
Hello. So does migration have anything to do with an actual change in the orbital eccentricity, how elliptical the orbits are? And I was wondering if you had a Jupiter, could you have a Jupiter in a different solar system with a different kind of elliptical orbit than the inner solar system had? Or is that
We
precluded?
already see Jovians in extremely elliptical orbits, and that could very well mean that there was another Jovian, they interacted, and one got scattered out and one got pumped up into a big eccentric orbit. They're now looking also at the motion of free-roaming planets, that there might be quite a lot of these out there, as a matter of fact. And they could have had scattering of incidents with pre-existing Jovian planets. If you had, say, Jupiter interacting with Uranus, I tell you which one wins. So that's a possibility. But could you have an eccentric Jupiter and something in an inner terrestrial orbit that's more circular? Sure, because this depends on what the periastron is.
So, but would that kind of Jupiter make life less likely? Or, I mean, if it was, would it perturb things more?
You know, I don't, the answer is I don't know. I haven't even ever considered that, so I'm not willing to answer when I might be talking out my, yeah.
But it's not just the ellipticity. There's plenty of evidence in the Kepler sample for Jupiters which are orbiting far more inclined to their ecliptic plane than, say, the gassy planets in our own solar system. So they probably have gone through some dynamical evolution, so much so that there's at least one example where we see a gas giant orbiting retrogradely. So every planet in our solar system orbits in the same sense that the sun rotates. In this particular system, the sun, the host star, rotates in one direction. This Jupiter orbits in the opposite direction, which again suggests that there was some dynamical evolution going on. And while I know nothing about the theories of all of this, my understanding is, reading a paper the other day, that the amount of bombardment which is either accrued or prevented by a gas giant depends critically on the inclination of the orbit of that gas giant. If something is highly inclined, then the bombardment is significantly larger than if the two planets are in the same plane.
We have a question maybe on the right side of the room here. Anybody over there? Nobody has any questions? Okay, down here in the front. Can you give me the microphone? Your mic's working again.
Sorry. Oh.
I think your mic's working again.
Thank you. A lot of the discussion today has to do with gas giants versus habitable terrestrial-like planets, but one of the great discoveries of the last 50 years are all the moons around the gas giants, especially Jupiter and Saturn, and how varied they are. What about the possibilities for life on these moons of the large gas giants like, say, Jupiter and Saturn? I mean, that seems to be that they're great candidates.
Okay, I can take the moons of Jupiter question. In fact, if you look at the moons of Jupiter at the Galilean satellites, you can see almost like a mini solar system, as Io is the rocky body with the heavier elements, and then you have the more icy bodies outside, Europa, Ganymede, Callisto. Now, we think that Europa is one of the most promising places for us to find life. And that's why so many scientists are so interested in sending a mission to Europa. And in fact, the European Space Agency has approved a mission to Ganymede that's also going to look at Europa. Now, we know Io has volcanoes because of the peculiar orbit it's in, that it suffers from the gravitational attraction of Jupiter on pulling it one side and the other Galilean satellites pulling it on the other side, to put it in simple terms. But the same tidal forces that actually make Io be so volcanic also heat up Europa, but to a lesser degree. So we think that there are actually underwater volcanoes in Europa. Europa has an icy crust, an ocean of water under this icy crust. And if there are volcanoes, as we think there are, underneath, you have heat and you have water, and those are two of the key ingredients you need for life. So maybe in other moons of other objects, like Enceladus, the Cassini mission found that Enceladus has volcanism. And it has plumes of materials, again, an ocean of liquid water, water vapor coming out in plumes, and again, might be a very good place to look for life. And I think our astrobiologists may be able to elaborate more on that.
Well, I think you did a very good job of covering it. I mean, Europa certainly is the two prime candidates for looking for extant life outside the Earth in our solar system are either deep under the crust of Mars or in the oceans of Europa. And Enceladus is of interest too, but Europa sort of fits things most perfectly, and since we can't, so we look at that and assume all the rest are like it. For Jovian planets in habitable zones, there certainly exist, and there are certainly non-trivial numbers of them. And I think it's worth saying that one of the next steps past Kepler in 0-0, right? It's soccer. One of the next steps past Kepler, once Kepler finishes wrapping up, and there's sort of a pause because Kepler did a very good job of answering the question it was asked of, and was the question everyone had been answering. So what do you ask next? And one of the questions is going to be, well, what about all these Jovians in habitable zones? Do they have moons around them? It's a harder question. I think it's solvable based on what I hear people that do this sort of thing say it is. What it'll take, I don't know, but that's going to be one of the next key questions, because there could be a lot of habitable worlds tied up in moons around gas giants in the habitable zone.
Next question? In the back?
I've heard that one way to find life is to look in volcanoes, or that to have life, you have to have volcanoes or plate tectonics. Can we tell that any of these exoplanets have plate tectonics or volcanoes, or are we anywhere near to being able to determine that?
Observationally, directly, the answer is no. Computationally, theoretically, philosophically, of course. Tectonics, I believe, are the result of all kinds of effects, both internal and external. And we expect and predict these things to go on across many exoplanetary systems. But directly detecting such behavior, no, we don't have that capability yet.
I would just add that, in fact, you don't need plate tectonics in order to have volcanoes and Io. And in fact, we have found no evidence of plate tectonics anywhere else outside the Earth in the solar system, which perhaps is surprising. But it is thought to be because the Earth has just the right thickness of crust relative to the size of the planet. And if the crust is too thin, it just sort of breaks up completely. If it's too thick, like we think is the case for Mars, then plate tectonics can try to get started. And Valles Marineris may be an example of that, but it just doesn't get going because the crust is too thick. But it doesn't mean that you can't have volcanoes. And in fact, we see volcanoes on Mars and Venus, and active volcanoes on Io, etc. So it's just a clarification.
Another clarification is, okay, the theories of the origin of life involve areas around volcanoes, basically where water comes in, meets the hot rock, and you get interesting chemical reactions going on. One of the theories for why Mars is currently uninhabitable is lack of plate tectonics. What can happen is if you don't have plate tectonics, you're not pulling your plates down below the crust and melting them. So your CO2, if you've got liquid water, which you need for life, it's going to react with the rock. It's part of weathering the mountains down, and it forms these carbonates we see all over the planet. And all that gets pulled out of the atmosphere, until it gets pulled under the crust, melted, and the CO2 gets released in the volcanoes. If you stop that, you just lose all your CO2. And before life, CO2 and nitrogen are your big things in your gases. And there's ways you can lose nitrogen too. So if you lose all your atmosphere, in high school you're all shown how if you lower the pressure, the boiling point of water gets lower and lower and lower. That can get low enough that water boils the temperature that's below the temperature it freezes at, which means you can't have liquid water. That's what we mean by the triple point. And that's generally why Mars is uninhabitable on the surface. The deep crust is another matter. So plate tectonics is considered very important for the origin of life. Now, one of the requirements is thought to be water, which is also a requirement for life. I don't know about crust thickness. That's not my my pay grade, I'll say. But volcanoes, of course, are planets form hot, and the heat has to go somewhere. So volcanoes are a given. Plate tectonics are important. I kind of think they're going to generally be likely on planets that have water, but they are probably necessary.
One thing that as far as plate tectonics, I think we've discussed that, but as far as volcanism, I want to mention one thing, that what a planetary scientist calls a rock strongly depends on where you are in the solar system. In the outer solar system, ice is a major component, a major solid component of the crust of every moon, sans one, Io. So in the outer solar system, we consider ice a rock. That said, when you talk about a volcano, when you talk about what's magma, it's molten rock. So in the outer solar system, water would be what comes out of your volcanoes. So we have found evidence of, well, almost overwhelming evidence of volcanoes on Titan. Titan's surface is mostly ice. So some have postulated that a magma chamber on Titan could be a big cauldron of potentially life-sustaining water. Again, so when your notion of what a rock is changes, your notion of what magma is changes as well. Just throwing that out there. This is very highly speculative, but still, it's something
So
that we could
I hate to
consider.
cut off this interesting discussion,
Oh, it's
but
time.
it is 12 o'clock. If we could all thank our panelists one last time.
I wrote the whole paper on that.
I should have turned it to you, I'm sorry.
Enjoy your lunch. We'll see you back this
You
afternoon.
actually brought up the point of what is magma, you know, and the effective definition
Say a
of
few interesting
magma.